Hello everyone, my name is Zhang. Very pleased to be here to introduce our latest work enabling high-dimensional disk state embedding for generic failure detection system of heterogeneous disks in large data centers. I'm a chief engineer in Huawei and a postdoctor from the University of Amsterdam in the Netherlands at the Intelligent Data Engineering Lab. I achieved my PhD degree at Huazhong University of Science and Technology in China. Device failure is a common problem in large data centers, where hard disks are widely used as primary storage devices. Although there are a series of passive false defense mechanisms like the erase codes and RAIDs, many researchers have focused on proactive disk failure detection, which aims to ensure the reliability and availability of large-scale storage systems in advance. This year, there have emerged a decent amount of researches on disk failure prediction. Almost all hard disk drivers and flash-based SSDs come with built-in the self-monitoring analysis and reporting technology, SMART, which are indicators of disk healthy status. Each SMART attribute entry consists of 5 elements. A disk uses the so-called threshold method based on SMART values to claim its failure status, which means the hard disk would raise an alarm if the value of a SMART attribute crosses the corresponding predefined threshold. However, this threshold method only achieves poor performance. We observed 6 classes of approaches of disk failure detection. Threshold-based approaches, we refer it to as the TB, and distance-based anomaly detection approaches, DAD, and shallow machine learning-based approaches, SML, and deep neural network-based approaches, DNN, one-class classification-based approaches, OCC, and transfer learning-based approaches, TL. However, these approaches have their limitations as summarized in this table. First, limited applicability. Different disk manufacturers have different SMART values or data distribution, even in different disk models of the same manufacturer. This will result in a situation where methods trained on specific parameters only work well for the same manufacturer, and often even for the same models, limiting their scope of applicability in practice. And second, um, uh, lack of adaptability. New disk models entered greatly to replace or augment the storage capacity, leading storage system to consist of disks from the different vendors and different models. Fitting these different models must be retrained to obtain more reliable predictions in order to adapt to the change in the data distribution introduced by these new disk models. Such retraining is tedious and expensive in a large data center. Third, imbalanced datasets. In real-world cloud storage systems, the imbalanced ratio of failure samples and healthy samples poses a significant threat to the efficiency of machine learning models. And fourth, minority disk failure detection. In storage systems, due to a lack of sufficient training data, some detective approaches fail to deliver satisfactory detective performance for those methods. Although some transfer learning methods have been proposed to address this issue, their performance depends on finding a suitable source domain for knowledge transfer, which might be difficult in a real-world data center. Last, and poor detective performance. Most methods show unstable performance in practical long-term use and often fail to obtain both high true positive rate and low false positive rate. Before we introduce our motivation, we show some preliminary results first. We analyzed the overall performance of existing proposed approaches using different disk models from both the Smart Dataset, Tencent, and Backblazer. And this figure shows the overall detective performance of the state-of-the-art method SML, DNN, and OCC. In each figure, the x and y axis refers to the disk models, of training and testing datasets, respectively. We use FMISO to evaluate the performance of the failure detection models. The higher the value is, the better the performance is. In the last row of each figure, we use the hybrid dataset, which is the first 6 disk models for training and then detect on different disk models. Note that the last 3 disk models are not included in the hybrid disk models for training. We summarize the findings from these 3 figures. The first, the detection approaches built on the specific disk models only have good results tested on the same disk model. Moreover, DNN-based approaches shows the best performance in this case. The second, the approaches built on the hybrid disk models datasets decrease the detective performance compared to a model built on the same disk model. Moreover, the performance of these approaches further deteriorates when detecting the disk models that have not appeared in the training datasets. So, the same experimental setup, we also evaluate the method DAD. Although the overall detective result of the DAD method is not good enough to be deployed in practice, it is not sensitive to the different disk models. In order to investigate the detection for minority disks, so the minority disk is the number of the disks less than 1,500. For transfer learning approach, we use the majority disk model, which has the smallest KLD values with the detection minority disk model from the same manufacturer to train the detective models. This figure shows the result. The transfer learning approach delivers the best detective performance on minority disk failure detection, especially with the training dataset having smaller KLD values, while other candidates are difficult to handle this situation. In order to take an in-depth look at feasibility of this method in practical large storage systems, we studied the disk quantity by the different KLD values in 2 data centers. As shown in this table, most minority disk models only found the majority disk model with a KLD value greater than 1, which might result in poor detective performance. Therefore, it is still difficult to find the most suitable majority disk model with small enough KLD value to use transfer learning for minority disk failure detection. Before introducing our motivation, we first to answer the following 3 problems. The first, why the DAD approaches have good applicability and high adaptability while DNN does not. Because the DAD method learns the distance or the similarity between the normal and abnormal disk models in a certain space, which has a commonality and not sensitive to the disk models. However, the DNN approaches learns the distribution of smart data, which varies with disk models. The performance of this approach will decrease when the distribution changes. The second, why the overall detective performance of DAD method is not as good as other approaches. We think the reason is it performs the distance-based transformation and computation in low-dimensional space, but doesn't learn from the dynamically changed long-term behavior in high dimension. Last, why the DNN approach achieves the best performance among other candidates. The DNN is good at mapping the raw low-dimensional smart attributes to high-dimension target space through complex transformations that perform good expression and fitting ability and thus achieves better performance. So, considering the above advantages of the DAD and DNN approaches, we are motivated to apply the distance-based anomaly detection approach and deep learning to build a general disk failure detection system for heterogeneous disks. So this figure provides an overview of our proposed novel system, HDDse, which combines a sample pool, an LSTM-based siamese network for disk failure detection, and a decision maker. Sample pool is used to store the smart instances collected daily for each disk. LSTM-based the siamese network for disk failure detection is the core part in HDDse to output a binary classification result that indicates the similarity of these two samples. Decision makers is a model to map the sub-result of samples to the final whole disk healthy state. This figure shows the structure of the LSTM-based siamese network. We designed two LSTM networks to receive the two smart samples respectively, which need to be compared for the similarity. Note that these two LSTM networks share their weights in order to map the inputs to the same target high dimension space for comparison. The sample pool consists of the collected smart instances with the corresponding confirmed labels and some instances that need to be detected. We collect all the instances of each disk in the data center every day. All the time data have been discretely sampled at an interval of 1 day. The relationship between the smart instances, the samples, and the input training pairs is shown in this figure. As mentioned before, the input of our proposed networks are two smart samples in pairs. Therefore, we can freely combine and label a pair of samples from the same disk manufacturer. There are two benefits for generating this form of training datasets compared to existing approaches which treat each smart sample as a snapshot in the training process. The first, better with imbalanced datasets. It reduces the degree of the data imbalance by the simplest free combination. Our method effectively elevates the original data imbalance by a factor of 2. The second, better with minority disk models. It forms large training samples even with the minority disk models. Therefore, our model can increase the number of samples greatly and make better use of deep learning algorithms to detect the failure and avoid model overfitting. So each target detecting disk consists of several results of detecting samples at continuous moments. Each output result indicates the detection for a particular sample at one moment rather than the whole disk health state in a pre-out. Therefore, to improve the robustness of the detection model against noise, we proposed a voting-based sliding window method to make a disk healthy state decision for the final disk state. We use smart dataset from two real-world data centers for evaluation, Tencent and Backblazer. We use 5 metrics to report the detective performance in our experiments. Many researchers have proposed the MTDDL to approximate the mean time to data loss with failure detection model. However, this matrix neglects the cost of misclassification by the approach. Therefore, we proposed an end-to-end economic analysis matrix called the cost-based MTDDL. We refer to it as the CMTDDL, which considers not only the reliability but also the misclassification's cost. We use the T-distributed stochastic neighbor embedding technique, which can project high-dimensional embedding space into 2D spaces for data visualization while striving to keep data clustered together in the high-dimensional space, clustered together in the low-dimensional space as well. This figure shows the result. These two figures shows the results. The left figure highlights the challenges in failure detection of disks based on smart attributes in heterogeneous populations. As can be seen from the right figures, the healthy and failed disks are easily separated after embedding using our proposed approach. This experiment result shows that our method can generate a unified and efficient high-dimensional disk state embeddings for generic disk failure detection of heterogeneous disks. It's interesting to investigate the detective performance of HDDSE when only trained on minority disk datasets. We've compared our approach with the other 5 state-of-the-art approaches. It's worthy to note that our HDDSE achieves the best performance in all cases. The reason is twofold. On the one hand, the training pairs generated by our method are extremely large, which makes our model not easy to get overfitting. On the other hand, the disk state embeddings in high dimension learned by our design LSTM-based siamese network is effective for model classification. In order to investigate the model applicability of our HDDSE, we use the imbalanced dataset of 10 disk models from 3 disk manufacturers in 2 data centers to conduct this experiment. When dealing with the disk from the different manufacturers, data centers, and even minority disk models, HDDSE achieves high F-Michel values compared to other candidates. The reason is that our model maps low-dimensional attributes to a general high-dimension space that is not sensitive to the difference in disk models, which lead to the detection to be performed well using a unified distance calculation. We evaluate the adaptability of our HDDSE, which is how an approach can adapt to a disk model that has not appeared in the training dataset. This figure shows the result. Our method using different hybrid datasets all achieved better detective performance than other candidates. It indicates that our HDDSE does not need to establish or maintain a new model and owns strong adaptability that can completely adapt to a new disk model regardless of disk manufacturers, disk models, data centers, and minority disks. This table shows our approaches improves the cost MTDDL by about 2 orders of magnitude than the other 4 candidates. In other words, HDDSE greatly improved the reliability of the storage system at a low cost. This figure provides the filter time statistics for each approach. DAD has the lowest training time and the highest detecting time due to its easy training method and large computations of the calculating distances. Our approach's HDDSE takes the second highest training time followed by the random forest and the second highest detecting time followed by the DAD method. Considering the training task in a dataset and sometimes the detective models are updated weekly or monthly, so the time cost of HDDSE is acceptable. We last simulate practical long-term availability in data centers, Tencent. This figure shows the TBR and FPR of the different detective approaches in the following 15 months. HDDSE shows the higher TBR and lower FPR compared to the other state-of-the-art method. It's worthy to note that HDDSE exhibits the stable detective performance than other candidates. We attribute this to the LSTM-based network, which is well learned from the dynamically changed long-term behavior of disk status. So in this paper, we propose the HDDSE, an LSTM-based siamese network that can learn the dynamically changed long-term behavior of disk healthy status and generate a unified and efficient high-dimensional disk state embeddings from low-dimensional smart attributes for disk failure detection. It has good detective adaptability to the disks which have not appeared in training data center and deliver good performance for the imbalanced or minority disk datasets, thus improving the storage system availability. Furthermore, the proposed approach improves the reliability of the data center and exhibits long-term availability. Thank you.